Hey everyone. Sorry I'm not there with you today. Hopefully you remembered that I will be out today, tomorrow, and Friday, and I'll for sure be back next week when we come back on Tuesday. Remember, there's no school on Monday because it's Labor Day. Today I have a pretty routine set of expectations for you. We're going to start by taking the notes for lesson 4 Desmos, and then I'll preview lesson 4 Desmos today, and then you will do lesson 4 Desmos, the one titled Scaling Challenges. If you finish all of that early, then you could work on your homework. If you haven't finished it already, the one that's due tomorrow, unless you're in fourth period, then it would be due on Friday. I believe that's the Desmos Online 7.2.02. And if you finish all of that, then you could silently read for any remainder time you have in this class period. I shouldn't hear about people playing games or being disruptive if they finish early while other people are trying to work. Okay, with all that being said, let's go ahead and get started on these notes. You should already have your book open to page 13. If you don't, do that quickly now, please. And if you don't have your book, I made some photocopies of this page, just like the one that I'm using. And I set them somewhere on the front counters here. Go ahead and get yourself a photocopy of the page and just take the notes with us and then stick this page in your book whenever you're home or the next time you have access to your book. All right, we start with these 3 sentences where we're expected to fill in the blank. And I'm going to start with the middle sentence because I feel like that's the one that most people like kind of understand the easiest, and then we can go from there. It says a scale factor blank makes a scaled copy larger than the original. So in order to make a scaled copy larger than the original that it's copying from, you would need a scale factor larger than the number 1, or we can just say bigger than 1. Bigger than 1. Or if you prefer the word greater than, you could say greater than 1. Now, what this means is when you say you're going to scale something by a factor of 2 or a scale factor of 2, you're going to make it 2 times bigger. If you're going to scale something by a factor of 100, you're going to make it 100 times bigger. Now, if we go back to the first one, it says a scale factor blank makes a scaled copy smaller than the original. Now here we need a number smaller than 1 or less than 1 if you like that better. In fact, I think that's what I'm going to write. Less than 1. Now, with a little side note though, when I say less than 1 here, I'm only talking about positive numbers. We don't really do negative scale factors. I suppose there's a geometric interpretation you could have of that, of maybe things flipping upside down or getting inverted or something, but we're not worried about negative scale factors. So when I say a scale factor less than 1, I'm really talking about greater than 0 and less than 1. So decimals and fractions, like making something scaled to 1/2 would make it half its size. Scaling something to 0.3 would make it 3/10 its original size. And then the third statement says a scale factor blank makes a scaled copy the same size as the original. There's only one number that does that, and that's 1. So I'm going to write a scale factor of exactly 1. You multiply all the side lengths of something by 1, you're just going to get the same side lengths you started with, and everything's going to remain that original size. All right, now let's look at our 3 robots here. And this is a really good example of what you're going to see in today's Desmos lesson because it's all about these little robots and using a scale factor to make one robot the same size as the other. And what you're going to see in the lesson, except for one screen where I think they messed this arrow up, is they're going to draw an arrow from one robot to another to indicate which one is the original and which one's the new. So for example, our first challenge is to find a scale factor that would make robot A the same size as robot B. And now they want us to determine the scale factor between each pair of these robots. And so for me, I think if you say robot A to robot B, you're treating robot A as the original and robot B as the new. And so using this kind of reddish purple color I'm using, then that should be an arrow that looks like this, A to B, to indicate that. And so since A, the original robot, is bigger in this case, and B is smaller, we're going to need, I don't know why, I guess, okay, so I wrote new here on robot B. Oh yeah, okay, I don't want to write it on the robots themselves because that'll get confusing. Okay, so in order to make our original, in this case, robot A, small like our new robot B, we're going to need something smaller than 1. Well, we can just divide the dimensions we see. I'm going to take this 12 height from robot B and divide it by the 16 height of robot A. And now you might be thinking, oh, what's 12 divided by 16? I need a calculator, this and that. No, don't do that. In fact, fractions will make your life a little bit easier in the case of doing this. And that will actually be true a lot in this class if you get used to a factor I'm going to teach you on this page. So let's just stick with fractions. 12 divided by 16 is 12/16. A fraction bar means division. So 12 divided by 16, 12 over 16, same thing. Let's simplify it though. I know that 4 goes into 12 and 16. So I'm going to divide the top and bottom of this fraction by 4. 12 divided by 4 is 3. And 16 divided by 4 is 4. So the scale factor that if you think of robot A as the original and robot B as the new, then the scale factor that was used there was 3/4. Or in other words, robot B is 3/4 as big as robot A. Now, for the second question, I really want to teach you this very useful trick or fact that's going to keep coming up in this class. Like it's not just for this one thing. You're going to see it in multiple other topics that we cover throughout the year. And getting used to this pattern now is going to make stuff easier for you later. So try to catch on to this. But first, we're going to make a change. We're going to change this C right here to A. Yeah, my A doesn't look very good because my marker is too bold, but I am writing over the C here and turning it to A. And so what I want this question to say is robot B to A, or in other words, we're just reversing the question from before. Before it was, what's the scale factor to go from A to B? And now I want to talk about the scale factor to go from B to A. Well, just like before, I took the new height, which was 12, and divided it by the original height, which was 16. I'm going to do the same thing, but all that means is the numbers are just going to switch, right? This time, the 16 is the new, and the 12 is the original. So instead of 12 divided by 16, it's just 16 divided by 12 this time. And we can make a fraction again. Instead of 12 over 16, it's going to be 16 over 12. And just like before, 4 goes into 16 and 4 goes into 12. So we can simplify this fraction using 4. Divide by 4 on top, divide by 4 on bottom. And this time I get 4 over 3. And compare that to the scale factor we got in the first question. I'm hoping you see that they are, the fancy word is reciprocals of each other, but we can just say flips. They are the flips of each other. Because all we did is look at the question like reversed. We took the robots and went, troop. And so the answer goes, troop. And that's going to happen a lot in various things that we study in 7th grade math. So just kind of get used to that idea of, oh, we reversed the problem, so the answer got flipped. But this only works if you do the math in fractions. If you had done the math with decimals, like if this said 0.75 instead of 3/4, because that's what 3/4 is as a decimal, you couldn't really flip 0.75 to get this, because this as a decimal is 1.3 repeating. And there's no like really nice, easy connection you can see there. So like this trick is really cool, but it only works if you do your math in fractions. And then the last one says robot A to robot C. I hope you can see that robot A and robot C are the same size. And so that scale factor to go from here to here is 1, and we're not even going to bother writing that. Instead, we're gonna write in the summary area here, essentially the two like tricks or facts I need you to know from this note page. 1, scale factor equals new divided by original, and I'm writing divided by as a fraction bar. So new over original means new divided by original. And when I say new and original, I mean corresponding side length pairs from those robots or diagrams or whatever we're working with, right? So this 12 and this 16 is a corresponding pair because they're both heights. So new height divided by original height. It might not always be a height. It might be something else, whatever we're working with. And then the second fact I want you to know is this like flip trick. And writing what this is a little weird, but here's how we're going to write it. The reverse scale factor. Now, this is not a real thing. Sometimes Mr. Thomas will make up things that aren't real math terms to just kind of describe what we're talking about. Reverse scale factor is not a real thing. But what I mean by reverse scale factor is if you know the scale factor to go from one thing to another, the reverse scale factor takes it back the other way. Is always the flip of the scale factor, right? The scale factor to go one way. If the scale factor to go this way is 3/4, then the scale factor to come back this way is going to be 4/3. And that's going to be useful in today's Desmos activity. So in fact, I want to preview some of the slides for today's Desmos. Then you got the rest of the period to try to finish it. So let me close this document. Now you got my face all big on the screen, right? And then I'm going to share a screen with the Desmos. Okay, so the warm-up, I'd really like it if you guys are talking to each other on this screen. You're all going to start it together all at the same time. You're all on the screen together. Some people know how to do this stuff really well, and some people are kind of like, oh, they don't really know how to do this yet. But understanding this part will be kind of helpful for the rest of the activity. And so if you know you're the type that kind of understands this stuff, be mindful of the fact that I'm not in the room and I can't help everyone the way I would if I were there. So like talk about it with your group mates and explain it to them before everybody sort of moves on and starts working at their own pace and this and that, right? All right, so when you get to slide 2, I encourage you to just enter some silly numbers here. Like when you enter a number here for a scale factor, it's going to change how big the green robot is, and you can do some crazy stuff. But don't get stuck here all day. It's fun to mess with this stuff, but then all of a sudden you realize you wasted 8 minutes. Don't do that. Screen 3. So here they've used the arrow down here between SAM3 and SAM4 the way that I think it should be used. They're indicating that SAM3 is the original robot here and SAM4 is the new. And when you enter a scale factor here, the scale factor always acts on the new. You're telling the new robot how big to be. And so you need that the purple robot to shrink down to be the size of the red one. So you're going to need a scale factor smaller than 1 here. And then look, the next question is they just reverse it, right? And if you did the previous question in fraction form, then when you do this slide, all you have to do is just flip it. If you remember the trick we just learned in the notes, right? So it comes in handy. When you get to this one, you need to use a scale factor of 1/2. And what that means is you can just count the boxes of all the pieces in this drawing, like how tall are the eyes, how wide are the eyes, how big is the space between the eyes, how long is the antenna. And every time you count those, just draw it down below here, but with half as many boxes. Please use the line tool for any straight lines, not the pencil drawing tool to turn out way nicer. The only thing you need the pencil drawing tool for is maybe the circular part of the eyes. Be careful as you do this one, though. I'd like it if these turned out nice. This one, I think you'll be able to handle. This one, again, if you know the flip trick, the answer to this one is fairly simple. Now here, this screen is the one that I'm not super happy with the way they use this arrow down here between the green robot and the purple robot. Because on this one, whatever scale factor you enter into the box is going to affect the green robot. And that doesn't seem right to me because the green robot is supposed to be the original the way the arrow's pointed. So I don't know if that's just a mistake or if the Desmo sees it differently the way I do, whatever. But this one says repeated challenges. And each time you're just going to enter a scale factor that makes the green robot match the purple robot. And there's up to 20 that you can do here. And I would be super impressed if anybody does all 20. I think it's reasonable that everybody should be able to do, I don't know, six. Well, I think we should call six minimum, but challenge anybody out there that wants to do all 20. All right, I think that's pretty much all I have to say about this thing. When you get to the are you ready for more and you do this robot, if you want to be a little silly on here and draw me something funny, I'll take that. All right, I'm gonna stop talking. You got the rest of the period to finish it, and be ready to take the STAR test tomorrow or Friday, depending on when you have this class. All right, see you guys.